everyone. Thank you for coming. Thank you for attending to this talk, in which we are going to talk about, I would like to talk to you about ParallelStreams, which is one of the new features of Java 8. I work for a company, for a Spanish-based company, which is called Autentia. What we do basically is we help our customers to upgrade their skills, or maybe to upgrade their platforms, their projects to the new technologies. So that makes us to be updated to the last version of the technologies. So this is one of the things that makes mandatory for us to keep a very updated knowledge of what's going on. Especially we are focused on Java and iOS development, but in this case we have started to upgrade the skills of some of our customers to start doing some Java 8 things. Another of the things that we do is based on that experience with our customers. We also offer them some training, and this is part of the kind of the training that we give. We try to not give basic training, but we also try to give a basic underlying understanding of what's going on behind the technologies that we are doing. Well, we have been using Java 8 for a while. Java 8 it's been with us more than 1 year. How many of you are already using Java 8, more or less? Well, cool. How many of you are using Java 8 using their new features? That means, well, the rest, yeah, it's usual to have many people using Java 8 just by simply upgrading their JDK, but programming, coding the same way that they were using, or they were doing with previous versions of Java, for example, Java 6, or which is nonsense. We should try to get the benefits of all the new advantage that Java 8 comes with. This is some of them. For me, one of the most powerful features is not only lambdas, but streams, because it allows us to process data in a very different way. But which is the way that that users approach the changes? As I said, some of our customers, we have found that they simply do nothing. They upgrade the JDK, and they simply keep coding the same way that they were doing. But there's another kind of approach to using the new changes, the new features, that is using those new features for anything. That's what we call the golden hammer rule. Is if you have a hammer, everything seems to be a nail to you. So you are going to hit with a hammer anything that is moving. Of course, that's not the right approach for everything, or for any case. In this case, we are going to try to give some overview of which are the cases, the use cases in which we should be using streams or parallel streams, and in which cases it's maybe not the best scenario to do it. But to do that, we need to have some basic understanding of what we are using, and that's something that we try to always encourage to all the attendees of our training courses, or our customers, of all of our people attending talks like this one. So let's start by a very short review of what stream is, because I think that most of you already know what it is. Basically, what is defined as stream is a convenience method. This is the definition that I like the most. It's a convenient method to iterate over collections in a declarative way. And the key word here is the declarative way, because we are not going to do any kind of specifying the way that we are iterating over the loop, over the initial data set. But what we are doing is just simply writing what we want to be done over the elements that are belonging to the collection. Well, in this case, we could we are going to use a very basic use case. It's a very simplistic one, but it's going to allow us, even this simplistic example, is going to allow us which are the best scenarios to use parallel streams or which is not the best scenarios. It's very concise, it's very simple, but it's going to allow us to show a couple of really interesting things of how the streams and parallel streams work under the hood. So in this case, if we have an array of, let's say, 10 million numbers, we are going to apply some kind of processing, for example, by filtering which ones are even numbers. In this case, we could do this by filtering and applying a lambda just to check the modulus of the number. Well, if we could have an X-ray picture of what a stream is, basically this is the anatomy of a stream. A stream defines three parts. The first one is a data source. A data source could be a collection or could be any kind of data generator, like a function, for example, or like a way of specifying a range of data. We also have a set of intermediate operations which conforms will build up what we call the pipeline of operations. And this is basically the list, the chain of things that we want to be done with our original data set. So this is what we call, this is declarative programming style of programming, because we are just simply adding one by one the different steps of the calculations that we want to apply. And finally, we have a final operation, which is basically most of the time a collector, that is going to iterate. This final operation is the one that is going to start iterating over the collection. The way that stream works is by, it's not by iterating, the first operation is not iterating over the data source, but it's the final operation who is going to ask for the next element to the pipeline, to the chain of operations. And those operations are going to ask the previous one on the pipeline for the next element up to the data source. Well, about iterating, the iterating strategy is hidden inside the stream. That's what we are not in the need of specifying any for loop or using any iterator. We are just simply adding the different operations. So manual iteration, there's no manual iteration, so that means that we can focus on what should be done, not how we want to do it. And that means that we are getting the benefit of conciseness. That means that writing more readable code, shorter code, but just as short as it makes it more readable. And remember that most of the time, we as developers spend most time reading code than writing code. As I said, the elements are computed only when they are needed. Well, the good promise about the parallel streams is, given that the strategy of iterating over the collection is hidden on the implementation of the stream itself, we could probably change the way we are iterating by just changing underneath that strategy. And that's what in the JDK we have done for us. We have a different strategy for the streams, which are the parallel streams. That's what have been the promise of easy parallelism with the streams in Java 8. Because basically, we simply need to change the way we get the stream from a collection to another function, another method, which is ParallelStream, which is returning us a different strategy. So remember, as I was not iterating over the collection, the iterating strategy is given to me. This, in this case, is very easily for the developers of the JDK to change this default strategy. And in this case, the default strategy makes that I get the parallelism by removing and getting rid of any concern of handling threads manually on myself. Because we all know that writing threads and writing concurrent code on ourselves is not easy. And it's a burden to have to deal with things like break condition, deadlocks, threads, locks, and those kind of problems. For that, the default strategy, the ParallelStream, basically underneath is using the Fork Join framework. The Fork Join framework is a concurrency framework that was implemented in Java 7. We will get to that in a few moments. So let's try it. Let's try this brand new promise that Java 8 comes with in his latest version. Let's say that we have a set of 10 million random numbers, and we are going to apply a logic, a calculation logic, which in this case is going to filter those that are even, and we are going to sort them out. We are adding just this second step because we consider that sorting a set of elements is an expensive operation. So we could think that this is something that could be improved. The performance could be improved by using parallelism. So let's try it. Let's start with the sequential way of doing it. What we are doing basically is adding filtering and then sorting, and we are going to measure the time we are spending. I know that this is not the best way to benchmark some Java code. Benchmarking Java code could be tricky sometimes. In this case, even considering that this is not the most accurate way of benchmarking Java code, is going to allow us to see some differences, even not accurate to the millisecond. What I should do on a first approach when benchmarking Java code is just simply add my code on a for loop and give some iterations to preheat the JVM, to let the garbage collector interfere, increase the heap size if it's needed, to inline some of the operation here, and I start looking at what the results are after some iterations. So when I see that the numbers are more or less stable, I will try to keep this as a first reference. So this is in order not to burden you with any other benchmarking thing. This is the approach that I will use in this talk. In this case, the sequential thing is going to return me more or less half the initial data set in more or less 800 milliseconds using 2 threads. Well, that's not exactly the right number of threads that they are using. We will see that later. Well, let's try the promise done by Java 8. Let's convert this into a parallel string just by simply changing the method we are invoking. We are having the benefit of multi-threading, of concurrency, just to increase the performance, the overall performance of our algorithm. So that's cool. That's the promise that we have done. So that's a powerful feature. Which is our approach? Well, streams. Streams are a powerful feature. So let's use streams. Let's use streams everywhere. Even better, let's use parallel streams. Let's use parallel streams everywhere. And this is when things tend to get upset some people, because soon after you made a great promise, some people is going to take that promise for granted and is going to use that way, that simplistic way of adding concurrency to your data processing. And sometimes after Java 8 came out, things were not performing the way that it should be. So there were a lot of people complaining about use cases in which their performance was not better by using ParallelStream. Even worse, there are some cases in which using a ParallelStream could be even slower than using a for loop. So which is the case? Well, remember, try to avoid using a golden hammer for everything. And as we said, try to apply a motto that we have at the company I work for, at Attentia. We have a motto which is called, we don't allow any monkeys nor lizards in our company. And this comes from a talk with some mates, because one of the other things that we do, we also do auditing, and we review code from some of our customers when they call us because they are not getting the performance they expect from the project. So maybe they have hired the project to any other company, and the company has delivered the project, but they suspect that the quality is not the best one, so they ask us for some audits to find and solve some problems. And sometimes by reading the code of other developers, we go to the conclusion that you could even know the profile of the developer. And most of the time, you could feel that those profiles fit into two categories. In one category, you could have the monkeys, which basically is the kind of developer that is not worried about what he's doing. He's basically solving the problems because someone told him that was the way. Because he saw previously that the right way to solve a particular problem was to write code in a particular manner, in a particular way, and this is the same way that he's replicating. He's using the rule that monkey see, monkey do. That's the way I learn. I just repeat what I've seen others to do. And of course, this means that there are some developers out there, not you, not me, but there are some developers out there that which are simply repeating time after time the same way to solve problems, but the technology changes. The other kind of developers are the lizards. The lizards are a kind of animals that they have no brain. They have cool blood, but they have a very developed feeling of survival. So they have a very good instinct of what should be the right thing, the right way to do things. So this could be the kind of developer who is, well, I'm not sure if I should use a thread, but maybe if I have a synchronized block, maybe if I move this sentence out of the block, maybe it's going to work better, or maybe not. Well, I think you could do it, but I'm not really knowing what's happening underneath. And just move it, and things work out. So this is the kind of developer that you could find, because he usually adds add comments to the code in the sense of, don't touch this. This works. Don't touch this. It took me some time to figure out how should it work. I don't know how, but it works. Don't touch it. Well, this is the kind of developers which are called lizards. So by reviewing these two kind of developers, we found that we didn't want any of those kind of developers in our company. So we set up a rule and designed a sign which is called, we don't want no monkey, no lizards. And that means be conscious, know what you're doing, be consequent, know when you should apply any way to solve problems. And that means that you should be interested in not just what the framework, tool, or the language does for you, but how it does, in order to know which is the right moment to apply that. Well, in the case you are more interested about the story and the fundamental, it's more or less is written on a blog post. It's in Spanish. Maybe if you manage to learn to read Spanish, or if you use the Google Translator, maybe you could read the full story. By the way, if you like the story, you can approach later because we have some stickers with that sign. If you want it, just approach me afterwards, and I will give you some for free. Well, so following that rule, following that rule, that motto of no monkey, no lizard, let's see what's going underneath when we are using parallelism, when we are using parallel streams. So the first thing that we have done, we have said, is that parallel streams means that they give us, they return, the parallel stream method return us a method which is implementing, which is relying on a default strategy to iterate over the original data source. And this strategy is based on using the ForkJoin framework. How many of you know the ForkJoin framework? Well, less hand has raised. This is usual. This is usual. The ForkJoin framework is a framework that came up with Java 7, sorry, but it's proposed by Doug Lee, and basically it's a framework which was designed to use in those cases in which I could split the tasks to be solved in several simple and smaller tasks that could be solved in parallel. And maybe those tasks, those subtasks, could be also split into smaller ones. So this is the way that Doug Lee proposed to be included in Java 7. And this is what it's using parallel streams underneath. So we need to know how the ForkJoin works if we want to understand which are the best results the results of the performance that we are getting from a parallel stream. In this case, this is more or less the pseudocode, the algorithm, which is describing the way that the problems are solved in framework in the ForkJoin framework. The ForkJoin framework, what it does is basically check whether the task that I should try to solve is small enough to be solved directly, because it takes some time. Sometimes you could, if you want to arrange, if you want to sort a set, an array, sometimes by the time it costs to you by splitting the array into two smaller arrays, it's going to take more time, in fact, than the time that is going to take you to simply sort the array. So the first thing that we should check is the problem small enough to be solved efficiently, directly by a sequential algorithm? If that's the case, just solve it. Don't worry about splitting that into smaller pieces. But if not, what you should do is split the problem into smaller pieces, add those smaller pieces to the list, to the queue of things that you should solve to be solved later, and wait until those smaller tasks are solved, and once they are solved, just try to merge the results in order to return the final result. Well, this is as the algorithm that it was proposed, but how is it implemented in Java 7? Basically, in Java 7, what we have is an executor service, which basically is a pool. It's a specific pool that is going to solve problems that are modeled to be solved by the ForkJoin framework. That means that we have an executor service, which is called the ForkJoinPool. That executor service is basically having a pool of threads that we are going to see that they are workers, they act as workers. And those workers, those threads, are going to execute a particular task, which is called the ForkJoin task. Of course, the ForkJoin task is going to add the logic of deciding whether it should be the task should be split into smaller ones or not, or could be solved in parallel. So the way that we add those tasks to our ForkJoinPool is by using the execute method or by use the invoke method. And this means these two ways of adding a task to the pool make a subtle difference, because the invoke method is going to be synchronous. It is going to make the invoking thread to wait until the complete task has been solved, has been processed. The other one, the execute, is going to just submit the task asynchronously, and the invoking thread is going to continue the work. It will get a future in the case that the ForkJoin task is returning some value. So these are two differences that we will need to know, because the ParalleLStream, we will get into detail of how ParalleLStreams are implemented using the ForkJoinPool. Well, the second element is the ForkJoin task. The ForkJoin task is basically an abstract class, because we have two kinds of ForkJoin tasks. One of them is the recursive action, which is a ForkJoin task that basically is not returning a value. It's just applying some logic, but it's not giving any result. The recursive task is basically the kind of problems that should return a final result. Well, on top of that, we have the ForkJoinWorker Thread, which are basically the threads that are going to be created on our ForkJoinPool. This means that the ForkJoinPool is going to create those threads, and those threads are going to get their ForkJoin tasks from a queue. But in this case, the ForkJoinPool is not assigning a regular queue to the ForkJoin threads, to the workers. It's assigning some kind of a special queue, which is called a DQ. A DQ is a basic constructor. It's a new data structure that has been added on Java 5 that allows us to process a queue in a different way. A queue is basically a data structure which implements the first in, first out strategy. So we are putting the elements into the queue on one end, and we are getting the elements from the other end. So the first element comes in, the second element comes in, and the thread which is picking the elements, in this case the ForkJoin task, is picking them in the same order in which they were submitted. So in this case, our ForkJoinWorker thread is our invoking thread is going to put the ParallelStream is going to put the first task into the DQ, and the worker thread in the pool, the main worker thread or the first worker thread, is going to pick the first task. If he needs to split them into different ones, they are going to be added on the same queue that is using the ForkJoinPool, the thread. So if I get the first initial operation, I'm going to split them out into 1, 2, or 3 or more smaller tasks that will be added to the queue. And still, the worker thread is going to pick the next task, is going to check if it could be solved laterally, and in the case it is not, it's going to split them and add again to the different to the same queue. Well, the thing is that we have a pool of threads, and we are not having just one worker thread. So the other threads, what they do is they realize that one of the threads has an extra amount of work, while they are idle, they are lazy, they have nothing to do. So in the ForkJoin framework, what it could be done, the other threads are going to help his brother thread with his amount of work. But in this case, the other threads are going to pick things from the queue, but not from the same end that the original thread is picking the elements, but on the other one. And this is called task stealing, because somehow the other threads are stealing work from other mates, from other workers. of course, I will say that this is not task stealing, but task helping, or helping with tasks. But this is the way that they call to the strategy. So the fork join algorithm in Java 7, is the original one proposed by Doug Lee, plus task stealing. So when should we use the fork join? The fork join is a perfect fit when we need to do computation that are independent, that could be split into different parts. So if we think that the original data set on the stream could be split into different ones and could be processed by different threads in separate, and finally just merge them out on the final operation, it could be a perfect fit for the fork join framework to use in ParallelStreams. So that's the reason that the fork join framework is chosen for that matter. Well, let's try then. Let's try it. We had this ParallelStream version of our example, which was getting more or less 200, a little bit than 200 milliseconds, and it's using 9 threads. Well, we are going to prove a little bit the way we are counting the threads, because, of course, counting the active thread is not accurate. We want to see how many threads are participating in our pipeline of operations. So we are going to use, for that matter, a special method added to the streams, which is the peak. The peak method is going to just look at the different element that is passing through the pipeline of operation at this point, but the peak operation is not going to modify or alter the stream anyway. So this could be a good opportunity just to add logging, or to just, in our case, to ask the current thread that is executing that operation, that part of the operation, to add to a set. Well, if we could check the size of the actual threads that are participating into the ParalleStream pool. Well, if the second thing that we need to know is that the ParalleStream is using by default a common fork JoinPool. I told you that ParalleStream are using is using the fork join framework, and the fork join framework means that we should be using a fork JoinPool. A fork JoinPool is an executor service that we could create, but the JVM has by default a default fork JoinPool, which is created as soon as the JVM starts. And the fork JoinPool, the ParalleLStreams, are going to use that common pool. And that's maybe the basic point where our problems could come, as we will say later. Another thing that we could do is we could define the degree of parallelism that we are going to use for our fork JoinPool. In this case, we could use a special property. We could set up a special property to set the maximum number of threads that should be created by the common fork JoinPool that the ParallelStreams are going to use. So this is useful, for example, if we want to customize in some degree the number of the usage of the CPU from the JVM when using ParallelStreams. So in this case, if we run this same piece of code by setting the property to limit the number of threads to 4, and we execute and we log at the console, we will see that we are using 5 threads when we set up that we wanted as maximum as 4. And this allows us to know another specific way of how the ParallelStreams submit their tasks to the fork JoinPool. Basically, they are using the synchronous method. So this could be for us quite weird, because it's not corresponding what the number of threads they are using is not corresponding with the maximum number that we set up to use. But if we try to print out the worker thread names, we will find that we are also using the invoking thread. This is done because the parallel streams, by default, are using the synchronous invoking of the operation over the pool. So that means that the main thread, the invoking thread, should wait. But in this case, what is going to happen that the main thread could be participating in solving the problems like another worker thread. Well, another problem that we could have is the ParalleLStreams use the common Fork JoinPool. I think that's pretty clear by now. But the thread invoking ParalleLStream could be also used as a worker. And this overall way of working makes important to us to know a couple of things. For example, the ParalleLStream is synchronous on the invoking thread, so any other operation should wait until the complete set of operations on the ParalleLStream are solved. But most importantly is that any other thread, because we are using the common Fork JoinPool, and because the Fork JoinPool use task stealing, that means that as soon as we have we have a ParalleLStream using a heavy computation or a computation that is going to have a long time, that computation is going to be submitted to the common Fork JoinPool as a fork join task, and this fork join task is going to be split into smaller ones by the first thread, by the first worker thread, and it's going to be added to the DQ. But all the threads running in the common Fork JoinPool are going to pick to steal those tasks. So the workload is quickly spread over all the threads on our Fork JoinPool. But at that moment, if the whole set of operation is going to take a long time, if at any other place, at any other point of our code, we are also using another ParallelStreams on another thread, that ParallelStream is going to add also that amount of that initial set of operations to the common Fork JoinPool. And that means that that fork join task is going to wait on the TQ, or is going to be affected by the fact that other ParallelStream is running at the same time. Well, so could we modify the way that this ParallelStream, the strategy that the ParallelStream is using to submit their tasks in order to make that they do not use the common Fork JoinPool? Well, by default, the bad news is that in theory, you cannot do that. But in practice, by the way that the task stealing works and the way it's implemented, you could use a Fork JoinPool, a custom Fork JoinPool. The way we are going to do that is basically by defining our custom Fork JoinPool, by specifying the number of threads that we want for our custom Fork JoinPool. And we are going to basically have on a separate piece of code the initial ParallelStream that we would like to run. The only hack, the trick in this case is that this piece of code, we are going to submit it to our custom Fork JoinPool by a lambda, by using a lambda. This way, the main thread, the invoking thread, is not the thread running this piece of code, but is the thread that is going to run and to use the ParallelStream is the thread inside our custom Fork JoinPool. And he's going to split it and use the different subtasks on the same DQ that is what called on the ParallelStream. So that way, we are going to keep contention. And of course, by using our custom Fork JoinPool, we could also change the strategy that we want to submit our task to the pool. Well, in this case, we could see that the time that we have taking to submit the task is just 1 millisecond. And after that, we are using the number of threads that we set up for our custom Fork JoinPool. And it's contained, the work thread, the CPU is contained on the threads for that Fork JoinPool. So that means that any other parallel stream running another piece, any other thread running another parallel stream is going to not to be affected by the fact that these threads are already busy doing any other thing. Well, this is basically the benefits that we get from that. We have a specific executor service. We don't affect other parallel streams, and we don't affect the common Fork JoinPool users and other threads that could be running another parallel streams or even the common Fork JoinPool. Well, and we could also reduce the unpredictable latency on how, or the unpredictable time on how a parallel stream is going to take. Well, some other problems using derived from using the common Fork JoinPool are regarding the kind of things that we are doing inside our pipeline of operations. The way, by default, the common Fork JoinPool is set up to use as many as twice the number of threads that cores you have in your CPU. And this is basically done because one of the most well-spread numbers is that the maximum performance could be done in most systems by using by having as maximum twice the number of running threads, not waiting, not blocking, running threads that CPUs you have in your, than cores you have in your CPU. So that's the strategy that the default Fork JoinPool is using to set the number of maximum threads. So if you are going to run any piece of code inside the parallel stream, which is going to wait for a disk to read data or for a connection to establish, basically what you are doing is you are putting the threads from your Fork JoinPool into the waiting state. And that means that you are basically wasting CPU cycles on your cores. So basically, what in this case, we should use a custom Fork JoinPool for that kind of operations. Another thing is never use the same parallel stream inside one of the operations of another parallel stream, because it is the same thing, more or less, that using when you are using two parallel streams on different threads. In this case, look that we are generating random numbers, and we are also trying to do it by using parallel streams. And look that we are getting almost 22 seconds for all the computations to be done. But if we use the sequential version, the sequential version for the inner loop, for the inner stream, the time is reduced up to half the time. This is basically because you are removing the contention, you are removing the workload between the outer and the inner streams. Well, another performance problems that you could face when using parallel stream is if you are using, like we are in this case, native integers or native primitives for some parts of your code, because underneath here you have an original data set of integers, of objects, and for that lambda to be executed, you need to invoke the int value over the primitive, over the object to get the primitive. And then once you have applied the filter, you are going to again box that primitive into the object again to be returned to the stream. And in this case, this is going to put more stress on the memory and more stress on the garbage collector. Well, it also depends on the kind of numbers that you are using, but the thing is that you are boxing and unboxing all your elements just to apply one of the operations. For that matter, the streams basically allows us to convert the full stream into a stream of primitives. And in this case, apply all the logic using primitives, which is going to be faster, and then go back using the Voxxed method to the original set of integers. Look that we have even get better results with that. So in conclusion, the parallel streams promise us to be able to write concurrent code without never writing a thread or using an executor service, because underneath, the parallel stream is hiding that strategy for us. That's one of the benefits of the internal iteration, that the strategy could be changed as we need. But that means that we need to work how it works in order to know which are the best use cases to use a parallel stream or not, and how we could use. The other thing is, try not to rely, if you are using heavy computation, or computation that they are going to wait for some, or to put the threads in a waiting state, try not to use the common Fork JoinPool using the hack. And if you are working with primitives, try to convert those elements into a stream of native of primitives value in order to reduce the stress over the memory model. Well, of course, don't try, because you are working underneath with threads, even though you are not seeing them. Don't use threads inside your pipeline of operation, because it could be a mess. Anything is going to escape. Anything running inside a Fork JoinPool is not going to escape the Fork JoinPool unless you are creating by yourself another thread. Well, be careful, of course, with the nested parallel streams. And another final advice is, as far as you can, try to avoid using lambdas if you can. And if you can, try to move this lambda into a method and write here a method reference, because a method reference or just simply invoking a method, because that way the JVM is going to be able to inline the invocation and not reduce the thing that he needs to look up on the virtual table of the object where the lambda is relying, because the lambdas are basically implemented and by code by adding a new symbol to the virtual table of methods. So by using not lambdas but method reference or invoking methods, you are allowing the JVM just to basically inline the code and removing the need to do that extra virtual lookup. Well, this is basically most of the things that I wanted to share with you. I don't know, we have no time for questions, or a couple of them maybe. Any question? There's one, two. Let's start with you.
Just a quick question. How do you know if a task is small enough to be executed or not? How can you filter the task?
A task inside the parallel stream. Well, basically, if I understood your question, is how do you know how many Fork join tasks are used in the Fork JoinPool? Or
At the very beginning, you show a code.
Yeah.
You put basically if the task is small enough, then execute.
Yeah. Well, when you are using the fork and the common Fork JoinPool, you are the one that they were waiting that piece of code, and you should, if you are using the Fork JoinPool, not using ParalleStream on your behalf, I can show your code. You should make tests to know which is the small enough thing, I could see you later some tests. When you are using parallel streams, this is not done. This is done by the split iterator. The strategy that is using underneath is to using a split iterator. The split iterator has, as far as I know, has a property in order to set the size of the split iterator. That means more or less the number of elements in the original data set. To an active, yeah.
So you convert to an integer. Do you actually explicitly have to call box?
Yeah.
Will it not?
Yeah, because otherwise it's not going to be able to invoke the collector, because it's changing the box method is changing the type of the stream that is returning.
Yeah, I'm just wondering whether the stream would automatically do that.
Sorry?
I need to try.
Yeah, but if you remove the Voxxed, the code is not going to compile because the collector should be invoked. You are using a toList, and the toList get the inference of the kind of elements that it's having on the stream by the last type of a stream that is returned from the last operation in the pipeline. So.
I'm just thinking that wouldn't the compiler also box into integers?
Okay, guys, it's time. We can continue this conversation afterwards, and look for me, and I will try to show some code that I have to, for example, find the small enough for an array thing. Well, thank you very much for attending. And